The Lorentz force is an electromagnetic force experienced by a charged particle in an electric and magnetic field. If the electric field is zero, and we will assume it here, then the Lorentz force is purely magnetic force acting on a charge as it moves through a magnetic field. The cause of the Lorentz force is a moving charge in the magnetic field. No moving charge or no moving magnetic field, then there is also no Lorentz force. Moving Lorentz force perpendicular to the magnetic field. Let's take a negative charge electron and send it from left to right through a simple homogeneous magnetic field. The magnetic field points out of the screen here. The Lorentz force points upwards in that case, and moving electron is therefore directed upward. If on the other hand the electron moves from right to left in the magnetic field, it is deflected downward. What happened if we change the magnetic field direction by 180 degrees? Now the magnetic field points into the screen. If the electron moves from left to right through this magnetic field, it is no longer deflected upwards but downwards. Determine Lorentz force direction. Let's first learn how to determine in which direction the electron is deflected. For this, we use the so-called left-hand rule. The thumb point in the direction of the movement, i.e. to the right, the index finger point in the direction of the magnetic field, i.e. into the screen, and the middle finger point downwards in this case, indicating the direction of the Lorentz force. The electron is deflected downwards. If on the other hand the electron moves from right to left, then the direction of movement changes. The thumb now points the left, the index finger points again into the plane, and the middle finger now points upward. Lorentz force thus deflect the electron upwards. What if instead of electron, a positive charged particle such as a proton moves from the left to right? If a positively charged particle moves through a magnetic field, then we use the right hand rule. Otherwise, the application of the hand rule remains the same. Thumb points to the right, index finger into the screen. The middle finger, the Lorentz force, points upwards. So we can state the positive charges are deflected exactly in the opposite direction to the negative charges, and we use the right hand rule for positive charges. For negative charges, the left hand rule. Lorentz force Q equation. How can we calculate the Lorentz force as a magnetic force? Let's denote the charge of the particle with the letter Q. We denote the Lorentz force with Fm, the velocity of the charge with v, and the strength of the magnetic field with B. B is also called magnetic flux density and indicates how strong magnetic field is. The unit of B is Tesla. In an experiment, we can observe three things. 1. If you double the charge Q, then Lorentz force on the particle doubles. Mathematically, this relationship means Lorentz force F is proportional to the charge Q. If you double the velocity v, then the Lorentz force also doubles, so v is proportional to the Lorentz force. The same is true for the magnetic field B. If you double the strength of the field, then the Lorentz force will be twice as large. Other parameters such as the mass of the particle do not affect the magnitude of the Lorentz force. So we can write down a formula for Lorentz force. F is equal to Q times to V times B. If you know the charge Q, the velocity v, and the homogeneous magnetic field B, which is perpendicular to the direction of velocity, then you can calculate the value of the Lorentz force by the way Lorentz force has the unit Newton. Movement and angle magnetic field. You don't have the simple case where the charge flies perfectly perpendicular to the magnetic field direction. Here we see the magnetic field line from the side. Previously we had the case where a charge has perfectly flying at a 90 degrees angle through a magnetic field, but if it flies under an angle alpha which is not 90 degree, then we have to add sine alpha to the QVB formula. Remember, if the charge is flying at an angle to the homogeneous magnetic field, then you can see this formula, and if the charge flies perpendicular, then alpha is equal to 90 degrees and sine of 90 degrees is 1. This result is the original simple QV formula. Lorentz and centripetal force. We noticed earlier that electron moving to the right is deflected downwards in this magnetic field, but it is not deflected downwards abruptly. Let's look at what will happen after the deflection. Let's zoom out. We will see that the Lorentz force always acts like 90-degree angle to the direction of the velocity. This is what nature tells us. This has consequences what the electron is forced to circular motion. The result circular path has a certain radius r and depend on how large Lorentz force on the particle is. A particle which performs a circular motion and has the mass m is held on the circular path by centripetal force Fz. In this case, the Lorentz force acts as centripetal force. So set the formula for Lorentz force equal to the formula for centripetal force. QVB is equal to m times v square divided by r. We can cancel the velocity v one time on both sides. Then we can get a formula with which we can determine, for example, the radius r of the circular path. We can easily determine the radius of circular path, for example, in electron tube experiment. Determine velocity of the electron. It is much more difficult to find our velocity v of the electron. The derived formula perfectly suitable for this purpose. We rearrange it for the velocity v. If we measure a radius of 1 centimeter, that is 0.01 meter, and set a magnetic field for 5 millitesla, we get a speed of 8,791,000 meters per second. So the electron moves on a circular path with almost 30% of the speed of light. Here is an example. A uniform magnetic field P points horizontally from south to north. Its magnitude is 1.5 T. If a 5.0 MeV proton moves vertically downward through this field, the force will act on it. The kinetic energy of the proton is K equal to 5.0 into 10 to the power 6 eV into 1.6 into 10 to the power verse 19 is equal to 8.0 into 10 to the power inverse 13. We can find its speed from the relation K equal to half mv square, or v equal to 2k divided by m whole inverse equal. Then if we equation this, we can get 3.1 into 10 to the power 7 meter per second. That equation give f equal to qv b sine theta equal to 1.6 into 10 to the power inverse 19 coulomb into 3 into 1 into 10 to the power t meter per second into 1.70, which is 7.4 into 10 to the power inverse 12. Thank you.